everyone. We'll be talking about thermochemistry for the next couple of weeks. Today is our first lesson, and we'll be discussing the conversion of energy from one form to another. As you remember, the law of conservation of energy means we can't make energy, we can't break energy, we can only change it. We can only transform it from one form to another. So, when we talk about chemical reactions, we refer to, and here's where my arrow is, we refer to situations where we have chemical reactions that either absorb energy, so they take energy in, and we call those reactions endothermic. And we can also talk about reactions that release energy, give off energy, and we name those reactions exothermic because energy exits the chemical system. Okay? For our purposes and humans' purposes, we have found a way to use these types of reactions to do work. Okay? And the ability to do work, it means, and if you've taken physics, you know this, it's the energy that's transferred to an object that causes some kind of movement. Okay? And this is the basis of the Industrial Revolution. So, when we talk about, and I'm just going to scooch this up for a bit and make it a bit bigger. Okay? When we talk about thermochemistry, and here's where I'm at right now. Thermochemistry refers to the study of heat or energy changes. So when you think of thermo, think of thermometer, think of thermoses, think of thermal fleece. They all have to deal with temperature, heat, energy changes. Okay? So when I talk, and especially for us with respect to chemical reactions. So how I've already underlined or circled here, we're talking mainly about physical reactions, which involve changes of state, or chemical reactions that result in a new substance being formed. So if you took physics, you will remember the definition of energy being the ability to do work. And as I've already said, work is when we've transferred energy in order to move something. Okay? And just like I've said before, we can only transform energy from one form to another. So, as I've written right here, there's a couple of different forms of energy: chemical, electrical, mechanical, light, and heat. You should be familiar with most of those. When we talk about chemical energy, we're referring to the energy found in chemical bonds. Okay? So here's a couple of examples of conversions of energy. Okay, we take electrical energy and convert it into light with respect to a light bulb or plugging in any kind of lighted object. When we do a combustion reaction, we take that fuel, add oxygen, have a spark, and then that energy is converted into heat energy from a fire, right? So moving on, we've got a couple of different types of energies: kinetic and potential. So kinetic, just like anything like kinesiology, it's the energy of motion, so moving things. So let's go back to grade 9, particle theory. We know if things are warm, they move faster. We know if things are cold, they move slower. Okay? Now, this is the one where we are in there's my pen. Sorry. This is the one that we may not have discussed as much before, but when you hear the word potential energy, it's energy that hasn't happened yet. It's like when your mom or your teacher says to you, you've got so much potential, meaning you've got the ability, you haven't done anything with it yet. Okay? Same thing here with chemistry or with chemical bonds. That energy is sitting in the bond. Nothing is released or absorbed until you break that bond or make a new bond. Okay? And if you look in your textbook, I don't remember the page right now. I think it's section 5.3. There is a table of values of energy for each type of chemical bond. So for instance, there's a certain value for the carbon-carbon bond and a carbon-carbon double bond and a carbon-carbon triple bond. And it all has to do with the amount of energy stored within that bond. Okay, so think of it like a bank account. You've got money in the account. That money's not doing anything for you until you take it out. Okay, so it's like one big vat of potential energy, the money in the account. Okay, so moving up, we've got thermal energy, heat, and temperature. So these are three definitions that you need to be aware of. Thermal energy, once again, is the amount of kinetic and potential energy in a substance. So say I have 1 mole of, I don't know, methane. Okay, I've got 1 mole of methane. How much energy is stored between the bonds in a methane, and depending on the temperature that methane is being stored at. That is how much total thermal energy that amount of methane has. Okay. If I heat up the methane, it has more kinetic energy. And if I cool it down, it has less. Heat is the transfer of thermal energy from a warm to a cooler object. So you're transferring energy to something that's going to accept it. And temperature is a measure of the average kinetic energy. So for instance, if you look at your thermostat and it says a certain temperature in your house, 20 degrees, or in the case of my house, much cooler than that, because we like to keep things efficient here at the Fisher household. But that doesn't mean that every air molecule or every part of your house is at that temperature. That thermostat reads only an average temperature. Okay, so there are variations depending on where you're measuring. Okay, but it's an overall average. That's what the temperature is. And like I said before, with the law of conservation of energy, we can't create, we can't destroy, we can only change, we can only transform. So when we take a look at what we're analyzing here, we've got two situations. We've got the chemical reaction actually occurring. So A plus B, arrow, C plus D. That is our chemical system. So it's the reactants that are consumed and the products that are made. That is the system we're talking about. Everything outside of that system is referred to as our surroundings. Okay, so if we're doing an experiment on our lab bench inside of a beaker, the stuff that's happening inside the beaker is my system. Me standing outside with my goggles and my appropriate safety gear, I am part of the surroundings. Okay, so a good example of this is, say you're having a barbecue. The chemical system is the combustion reaction that's happening within the barbecue. So your gas, the oxygen, the spark, and then the products being the carbon dioxide, the energy that's produced, that kind of thing, water, and everything else is the surroundings. So the food you're trying to heat up, the grill that gets hot, the air outside of the barbecue that is warmer now, those are your surroundings. So we've got 3 types of system, okay? And those 3 types of system are an open system, closed system, and an isolated system. So the open system is one where we can gain or lose matter and gain or lose energy. So think of it this way. An open barbecue is an example of an open system, right? You can throw more steaks on the grill. You can lose heat to the outside surrounding. Things can go in, things can go out. Then you've got your closed system where you cannot lose matter. So you're kind of putting a lid on your beaker. You're closing your barbecue so you can't add anything else to that grill. But energy can still enter or leave. Okay, so it's not completely sealed. That energy can't come and go. All right. And lastly, we have what we refer to as an isolated system. This is the situation we assume. So in a couple of days, we're going to be doing math. And the math will require that this assumption that the system that we work with is isolated, meaning you're not gaining or losing any matter. So the amount of moles in your reactants and products do not change, as well as the amount of energy in your reactants or products does not change. So you've got a completely sealed system. Okay? So moving on. We've already kind of gone through the definitions of endo and exothermic, but I'm just going to revisit it one last time. So exothermic, EX, means exiting. We're losing energy from our system to our surroundings. So energy exits the system. Okay, so keep in mind when I say something's exothermic, I'm talking about the chemical reaction. Okay, so from the perspective of the chemical reaction is losing energy, meaning energy is a product. And that's what I'm saying right here, because energy is leaving the system to go to the surroundings. Okay, and when we take a look at this diagram here, so if you'll notice, I've got potential energy, and here on the x-axis, I've got the reaction progress. Okay, and this is going from reactants to products. Okay, and so when I'm talking about reactants to products, I'm starting with my original reactants right here. Okay, and you're going to see that there's a certain amount of potential energy that's held between those bonds. Ultimately, because we're talking about an exothermic reaction, my energy is released to the surroundings. So what that means is that my system has lost energy. And so the potential energy in my products right here is lower. So to bring you up to over here, let's take a look at the math. My difference in potential energy right here, okay, is negative because we're talking about the final minus the initial, and that is a negative amount. So if you ever see a delta potential energy as being negative, that is an exothermic reaction. Okay. And what I have here is when an exothermic reaction releases thermal energy, my surroundings gets warmer because my system has given energy to the surroundings. Okay. Now let's talk about the endothermic reaction, the reaction that absorbs energy from its surroundings. So my energy enters the system. So endothermic enters. Okay, and if you think about this from the perspective that you have to kick some energy in for the reaction to take place. So if we think about it from that perspective, we can say something like an activation energy, perhaps, in terms of biology talk. Okay, we have to kick some energy in. Okay, so usually these types of reactions are not spontaneous. You need to heat it up, or you need to put some work into this reaction for it to happen. So same kind of diagram, only opposite, if that makes any sense to you. Take a look. So my y-axis has the potential energy. My x-axis, once again, has my reaction progress, so from reactants to products. So let's take a look here. My reactants are on the bottom here. Okay, so here they are. And in this situation, because it's an endothermic reaction, we are pumping energy into the system for the reaction to go forward. And as a result, my products have a higher potential energy. So just like before, if we look at our delta potential energy for an endothermic reaction, it would be products minus reactants, so it's a positive. Okay, it's got a positive value. So if we take a look, during an endothermic reaction, the chemical system absorbs energy from its surroundings. Makes sense. So that means when we put energy into our system ends up having a higher potential energy. And that also means that the surroundings, which would be me or you or anything else outside of that chemical system, would be colder because we, or the surroundings, had to give energy to the system. So then, here's another diagram. Endo versus exo, once again, same thing. If I'm talking endothermic, heat is entering the system. Endo, enter. Okay, so since heat is entering the system, that heat came from the surroundings, my surroundings get cooler. If I'm talking exothermic, that means heat is leaving the system. So the surroundings get the heat. Heat is transferred to the surroundings, so my surroundings get warmer, my system gets colder. Lastly, when we take a look at comparing the energy changes, we can look in 3 different situations. So firstly, number 1, a physical change. So we know what a physical change means. A physical change means a change of state. Okay, so we've got a physical change. Then number 2, we're talking about a chemical change. So don't forget, a new substance is produced. So bonds are broken, bonds are made. We made something new. But left side still has to equal right side. So it's not like we can all of a sudden introduce a new element or a new entity, right? Lastly, we can talk about a nuclear change. And a nuclear change means we're changing the nucleus at this point. So this is nuclear fusion, nuclear fission, and ultimately when we change the nucleus, we are changing the identity of elements involved. So that's what I wrote right here. Once we change the nucleus, new elements are formed, and that's what we're talking about. So to bring home that message, for the most part, it takes the most energy to do a nuclear reaction, then followed by a chemical reaction because you're still making a new substance. And lastly, you're keeping the same substance, but you're changing the state. Physical energy change is the least in terms of quantity. And just to drive that home, hold up. Here we go. We got an example of hydrogen going through all 3 types of change. So if we take a look at situation 1 right here, the phase change, as you can see, we're going from gaseous water, so water vapor, to liquid water. And since you are cooling it down, my delta EP is positive. It's an endothermic reaction here, so endo, because it's a positive, right? And you'll see that it's positive 44 kilojoules per mole. Then, when we go to scenario number 2 here, a chemical change, we've got a synthesis reaction involving hydrogen and oxygen making liquid water. And since it's a chemical change, it also is endothermic because it's a positive, but as you can see, my number here is 285.8 kilojoules per mole. So that is higher than my physical change. And lastly, a nuclear change. Okay, so I've got nuclear fusion happening here with 2 hydrogen nuclei coming together and fusing to form a helium atom. And as you can see, we made a new element, nuclear change. And what you can see right here is that we got mucho potential energy happening here. Okay, so 1.7 times 10 to the power 9 kilojoules per mole. So that is a significant amount of energy, which reflects the amount of energy required to fuse 2 hydrogen nuclei. All right, and if we were to graph all of these guys on the same scale, we'd never be able to do the nuclear change in a textbook because the textbook would be 1,000 kilometers long. So as is usual, I am going to ask that you read the textbook just to reinforce what you just learned. And as also usual, here's some homework questions. And I just want you guys to know that we're thinking of you. We want you to stay on top of your studies. This is definitely something you'll need next year, so don't give up on us. If you have any questions, use the discussion Dropbox or email us through LMS directly. Take care of yourselves, wash your hands, and be good to your mom